Hello everyone, my name is Haiming. My presentation paper is about efficient data compression in stream processing. This paper is coming from Microsoft Research, University of Toronto, and Johns Hopkins. So, first, I want to talk about why I choose this paper. I think because this paper is the first systematic investigation of the system of the stream processing with data compression. So what they do in this paper? So they first they identified a set of factors that influence the benefits and overheads of compression. Then they demonstrated that compression can be effective for stream processing, both in the ability to process in large windows and in throughput. What the methods they use? In this paper, they remove major sources of efficiency to improve the throughput, and they use hardware acceleration to reduce the cost of compression or decompression, and they direct execution on compressed data that leads to a further 50% improvement in throughput. So next, I want to talk about what is stream processing. So streaming is a constant and continuous flow of event objects that navigate into and around companies from thousands of connected devices, IoT, and other sensors. So stream processing is a process of being able to quickly analyze data streaming from one device to another at most instantaneous read after it's created. Uh, Streaming processing plays an important role in multiple different applications such as IoT, Internet of Things, clouds, and big data. In those areas, they all face the same issue, which is huge volumes of streaming data with real-time processing requires enormous pressure on the capacity and bandwidth of several memory. So in order to improve this situation, in this paper, they try data compression in stream processing first. They ask the question is data compression useful for streaming? So intuitively, streaming with simple operators should be bandwidth bottlenecked, either network level or memory bandwidth level. So in order to confirm the intuition, they perform an experiment with the state of the art streaming engine chair, which is used in Microsoft. It's a very simple experiment. They take real query over large column data with 8-byte integer field. Something like a query described here. Where query to check the error code is 0 or not. So as it simple as can be. And the expectation is it should be memory bandwidth bottlenecked. And if in this case, we can probably try to use compression. Well, the result is quite disappointing. What we observe here is that the compressibility doesn't necessarily mean performance. A scenario with no compression, which field is 8 bytes, and the compression here is just take each field and convert from 8 bytes to 1 byte. Here you would see observe if its memory bandwidth to see significant benefit, but the benefit of 8x compression gave you only 10 to 15% percentage performance improvement. So clearly there is something going on. In trail streaming engine, it doesn't let you benefit from data compression or any other techniques that improve their memory benefit. So what went wrong? First of all, the trail is written in C sharp, so the memory allocation overhead is out of control. And then There is a lot of overhead coming from memory copy and relocation. These two things takes about 2/3 of the time of execution, which is ridiculous. And the efficient bit wise manipulation and hash tables manipulation use a lot of streaming. So what rolls together cause a huge efficiency in process engine. So how do we improve this? This is another example. We add the benchmark from Steam Shoot. For example, the streams have multiple different benchmark. So the benchmark from Stream Shoot, the code is based on C++. So they have you they is so what you're gonna say is with the same number of threads, if we do the same thing, this is an ideal comparison with 8x compressibility and low overheads. Just the benefits of pure compression. This is a compression version. So we're able to say up to 7.6 speed up with 8x compression. So this is very good just to change the benchmark. So after the experiment, some conclusion that if you want to have an efficient stream engine, you have to do three things. Uh, First, you want to have fixed memory allocation because it would let you control how much time you spend on memory allocation, and efficient hash map primitives and efficient filtering operations. If these three prerequisites can be done, then the compression can be actually promising. This is the key observation during the experiment. Memory bandwidth becomes the major bottleneck if streaming is properly optimized. Dominant part of data is systematic in nature and hence a lot of redundancy and the redundancies can be exploited through efficient data compression. So with the key observation in mind, they built a prototype system called TerseCades, a regular stream process engine. This is a system overview of TerseCades. When the event stream coming, it immediately compressed and stored in the compressed data story. After that, uh, we need to imply different operators on compressed data. Every time when we need to access this data, we need to do decompression first. So this is essentially a higher level overview of the design. So next, they make several key design choices and optimizations. The first one is however, the question is which algorithms to use. In this design, they use lossless compression algorithm for the most part. In the lossless compression algorithm, they found that for these systematic data sets, it's better to use a arithmetic compression algorithm like base data encoding instead of classic dictionary based compression because they are very heavy, especially the decompression is extremely heavy. The overhead and the performance and kills the benefits of compression. And the lossy compression without output quality loss can be useful if you can guarantee there is no significant quality loss, and there is also possible if you put certain requirements on algorithm to test. Obviously, after showing one of the previous motivated graph. Comparison, decomparison, overhead is always added to the computer. So you want to do everything possible to reduce the overhead. So what they try to do is hardware-based acceleration of comparison, decomparison by using vectorization GPU FPGA. And last year, they tried one much more radical optimization, direct execution on compressed data. Let's go through to say a few of those choices, more details. For lossless comparison, they use Bell's data encoding algorithm. It's a very simple algorithm. Essentially, what it does when you get a set of similar wedges with no dynamic range. For example, this is timestamps, and those timestamps almost all streaming data have them. What do you do? You find some base, and everything else stored as an offset at data from this base. Example over here, you see some small variation in timestamps. Instead of storing them in fully just a story in a small small data here that allow you to easily get the data compressed. Why is this algorithm especially good for streaming? Well, it has extremely faster decompression. You can decompress it. Oh, sorry. You can decompress the data with just doing a vector addition. Just take this base and add the offset of the data. You can get all your data back. Thickness. Both comparison and depricing has a relatively straight forward implementation that can take up to 5 to 10 cycles. And of course, it's important to observe that it actually gives you a good compression ratio. So this algorithm can actually be useful. So for lossless, for loss comparison without quantity, output quantity loss in the integer space, we use base delta encoding modification if we know the range of the values and the places we need. And in the floating space, we use ZFP is coming from HPC domain. This algorithm is that allows to guarantee you the prices you get after comparison. And for comparison overhead reducing, what we use is SMD, vectorization, GPU, and FPGA. We observe that all of them can give you amazing throughput, especially for base data encoding. A simple SMD vectorization gave sufficient enough bandwidth of decompression. And the new idea that they announce that you called execution on comparison. As previously said, if you keep the data in comparison form, every time you need to communicate with processor, if doesn't and it doesn't really understand that the data is compressed, so you have to permanently compress and decompress the data. So it's a lot of overhead, both in terms of latency of compression and decompression, and of course, it's a higher engine overhead. So one question they asked here is can we leverage data being in a condensed form? The answer is yes. For some queries, Here is one common example that they show us how this idea works. So you have a classic key value story like this, and a story of values in memory in 8 bytes. Then execution the compression on those value with built data encoding algorithm. So it will store the metadata here and some small values, 1 byte data. So what happens if we run a simple query in baseline case? Let's say baseline case without comparison. In order to search if we have n values, I need to have n 8-byte comparisons in order to find whether the value is matching or not. Why is this comparison version is better? Because in metadata, it's already storing some information about the range of data. For example, if we search a value like 2000, and this metadata is from 0 to 1000, so we can completely avoid any comparison for this value. But what is interesting here is that even if the value within the range is still be better, that the value now be better that the value now instead of comparing for 8-byte values only need to compare 1-byte values, which was user vectorization. We can reduce the number of comparison. So no matter whether the value happen in the range or not, we either just a single comparison and divide by 8 comparison, which is significantly better than baseline. So in this way, having data in compressed form is actually not a burden and actually can be benefit. So as the result, we observed that you can actually execute compressed data. You will have much lower latency because you are completely avoid decompression. But you can also do either single compression and lateral compression. It would lead you lead the case when a wheel can run much faster than baseline. Then about the evaluation methods in this paper, they use CPU, GPU, and FPGA for hardware acceleration. So start with micro benchmarks. I will show you before and add benchmark from Steam Shot. This is a result based on Steam Shot benchmark. The x dimension is the number of threads, and the y dimension is throughput measured in millions of records per second. And at the bottom, this is a long compressed version. Here the blue line is ideal compression at x. The red line is a compressed line, and the green line is where applied vectorization. So what you can see here is that the vectorization is very helpful. It makes you close to the ideal. It makes you close to the ideal case. Increasing number of threads eventually become falling memory bottleneck, so it cannot benefit as much as before. But this is another example from search benchmark. So what is interesting here is that what happens in when direct execution. This is baseline without comparison. This blue line is ADM comparison, and this is a comparison with direct execution, the pupil line. Okay, so for search benchmark with direct execution, it's not only improve this throughput, actually it's much faster because we actually do this decompression. Thanks to the data in compressed form being useful rather than being a burden to decompression. So, in this paper, they not only implement this on Maker benchmark, they actually implement this streaming engine on several different realistic queries. One of those work they used in monitoring and troubleshooting is called PIN-MIS. What is PIN-MIS? PIN-MIS is just a monitor some byte nodes which are not well reachable. So here is the result. Yeah, this is different designs. This is throughput. This is trio. It has 3.2 million records per second. This is not optimized version, which we they just take the trio and modify the code a little bit, and then they left are all optimization. Without memory allocation problem, it finally become memory bandwidth bottleneck. And the lossless optimizer has different optimization. So overview, the total of the more than 50x improvement in throughput due to the data comparison with efficient optimization, which means it allows us to replace 15 machine with just buy one machine to run analysis on the regular basis. This graph is about performance of individual operators, which are applicable for real query, but not to group apply. That's why real query improves much more than group apply compared to the baseline. So they also apply different IoT datasets like geolocation data and weather data. The result shows us there is significant potential of compression without significant loss accuracy. So the summary is can data compression be effective in stream processing? So in this paper, the answer yes. The TerseCades design is a proof of a concept. Properly optimize the baseline system, use network data compression algorithm with hardware acceleration, and directly encode uncompressed data. And the results on troubleshooting workload used in production allow to replace 15 servers with just one. So it's that's it. This paper.